Hi everyone. This is the first video into the electromagnetic waves research. Here we're going to talk about electromagnetic waves, how they are created, and then in the second video we're going to talk about all the different types. So let's start off with how electromagnetic waves are actually created. So we have to go back to an atom. In an atom, electrons normally are found in the lowest or ground level. In case you guys forgot, there's three parts of an atom: a proton, neutron, and electron. The protons and neutrons are in the middle, and the electrons are normally found on the outside. So far, we've talked about the electrons just traveling around the fence, but they don't actually have to stay in their particular cloud or level. They can actually change levels. There's a few different ways that they can actually get to higher levels. They have to absorb energy. And there's a few different types of ways that electrons can absorb energy. You could heat them up. You also have chemical reactions that can give them more energy. You could physically collide them and force them together. There's a few different ways for these electrons to gain energy. Once the electrons absorb energy, we say that they're excited electrons. All giddy and excited. They're so full of sugar. Electrons eventually release the energy and return to the ground levels. The release of energy from a high level to a low level emits a photon. And here's a little bit better clarification of that. So here we have a basic picture. Here is a basic atom with the electron, if you would, just going in the outer level. So right now, according to this picture, the electron is excited. Here, you could see the electron jumps back down from the level to the ground level, the bottom one. And you notice that there's a little wave getting emitted here. So at this point, the electron is back down, and a little photon is emitted. I almost want you to think about this as a little kid on a swing. I'm sorry, not a little kid on a swing, a little kid on a slide. Imagine this is the little ground, and here is the top of the slide. So when you get to the top of the slide, you're all excited. Yo, I can't wait to go down the slide. This is going to be the best 20 seconds of my life. Nothing will ever top this moment. And then you start to go down, and you're like, whee! And then you're on the ground level, and it's like, okay, that was cool. And then you can choose to either do it again or stay there. So the wee, the you yelling, that's the photon being emitted. So obviously, if your slide is really small, you're going to be like, wee. But if you're doing like a roller coaster-esque ride and your slide brings you all the way up really, really high, the wee that you're going to let out is like, wee! And really high energy. So the bigger the jump from high to low, the more energy this particular photon will have. So photons have specific energies equal to the change in levels of that electron. And a photon is a packet of electromagnetic wave or an electromagnetic radiation. So here's more of a visualization of what a photon looks like. Electromagnetic waves are created by electric fields and magnetic fields perpendicular to each other. You guys may remember the right-hand rule from back in March. You know how your thumb is the force on the magnetic field or the force on a particle moving. So you could see, based upon the code here, how as the wave goes on, these two fields are vibrating back and forth, if you would. They're related to each other. That's why it's called an electromagnetic wave, because you have an electric field and a magnetic field present at the same time. So what's really the big difference between EM waves, electromagnetic waves, and transverse waves? Well, EM waves are non-mechanical waves, meaning that particles do not actually move. Once again, EM waves are just a release of energy. So there's nothing physically moving that you can actually measure. It's all an effect. It's an energy. Whereas transverse waves, the ones we've been focusing on, they're called mechanical waves. If there's no one there to move, then you don't have a wave. Think of it as if you're in the stadium, if you would, and people are doing the wave, you need people there to actually do the wave. You can't have an ocean wave if there's no ocean. So EM waves are considered non-mechanical waves, and the transverse waves, the ones we've been focusing on, are mechanical waves. You physically need particles to move. Well, since you need particles to move, you could think of this as like dominoes. So waves, normal waves, travel really fast in solids because all the particles are close together. So when one particle pushes on another one, the transfer is happening very quickly. So the waves go the fastest in solids, liquids, and then gases. And for the record, they can't move in space. So there's a lot of things going on here. Number one, you probably sometimes feel a vibration way before you ever hear the sound. This happens on trains. If someone is vibrating the cell phone, you could hear the table vibrating more than you hear the phone vibrating, because the vibration is making the table shake, and that's making you shake, versus the cell phone vibrating the air, which is a gas, which takes more time to reach you. This is why also in the sci-fi movies, you're not supposed to hear anything in space when there's an explosion or anything like that. However, because EM waves are pure energy and they don't require actual particles, they move the fastest in space. And then they slow down a little bit in the gas, they go slow in the liquid, and then they go the slowest in the solid. That's because now there's particles in the way that can absorb the EM waves, and it slows them down a little bit. You could think of this as if you were a person in an empty hallway, you're going to go the fastest. And if there's a gas, that's like an occasional person that's in the hallway with you, so you could still go pretty fast. Very small chances you're going to interact with them. Liquids, there are more people. And solids, it's like a pure traffic jam. You really have a hard time going through that hallway. But we are talking about waves, so something that they have in common, they have properties of waves. So frequency, wavelength, amplitude, the properties are still going to be there, just how they function will be different. So the speed of photons, aka EM waves, aka light, is 3 times 10 to the 8 meters per second in the vacuum of space. So this is actually the fastest that any EM wave will go. 3 times 10 to the 8. You guys will be given this value because it's so special to us. The equation that you guys have always heard before, E equals mc squared, well, that c is actually the speed of light, 3 times 10 to the 8. Just like how the number pi is 3.14, c, lowercase c, stands for the speed of light, which is 3 times 10 to the 8. And according to Einstein, you probably have heard of him before, this is actually the cosmic speed limit. Nothing can go faster than the speed of light. This number, once again, will be given to you. And then besides the actual waves going, sometimes they have different behaviors depending on how they go from one surface to another. The two that I'm going to focus on with you guys is reflection and refraction. Okay, very two similar words, but they have very different meanings when it comes to waves. So let's imagine reflection is when a wave bounces off the boundary of a medium. For the record, a medium is just a different state of matter. So for example, air to glass is transferring from a different medium. So in this case, if a ray comes in through the air, it hits the mirror, which is a different medium, and then it bounces off, similar to throwing a ball against a wall. Okay, they'll just bounce off. And the special thing about mirrors and other things that reflect is that the angle it comes in at is the angle it bounces off. For anyone who's ever played basketball, you guys very much understand this. Ping pong, same kind of way. The sharper it comes in, the bigger it leaves out. Okay? And that occurs when you go from one medium to another, and that particular medium has like some sort of shininess to it that does not absorb the energy. The other thing that could happen is this thing called refraction. And refraction occurs when a wave passes from one medium and they physically go through another one and change the path that they take. So for example, we have a light beam over here, it's in a straight line, but then it hits this piece of glass at an angle. And you may see the angle, once it changes here, it changes because it goes from one medium to another. And then when it goes back out again, it changes again. This is why people actually wear glasses. The wave of the light is going through the air. It hits the glasses that are on your face. They change the angle ever so slightly so that they go into your eyes at a different spot. This is my turtle. His name is Sal. You can say hi to Sal. I only have one turtle, not two. But in this picture, it kind of looks like I have two turtles. And you can't even tell where exactly he is in his turtle tank. Because if you think about how this picture is set up, if you look on this side, well, you went from water through glass through the air. But here, you go from water, glass, air. I'm sorry, just change that around. Here you go from water, glass to air. Here you go from water, air, glass to air, because this is above the water and this is below. So because of how the wave refracts, it looks like my turtle is in two actual spots. Only one of these spots is actually the true one. So that's another way that you've seen refraction before. Another example here is actually when you see sometimes the sun on the horizon. The air is one medium and space is another one. And because of the curvature of the atmosphere, sometimes it appears that things like the sun are not actually in the spots they are. So when you see sunrise, if you would, you think the sun is straight ahead. But because of the waves refracting through the atmosphere, the sun is actually below, physically below your line of sight. And it's the curvature of the waves that make it appear higher than it actually is. So that is why sometimes when you're looking at the sunrise and sunset, it seems to happen very quickly. Oh, all of a sudden there's the sun. And then as it goes above you, it tends to move a little bit slower. That's because really when you're seeing it over here, it's really low in the ground below you, and then it's snapping up in position to actually catch up with where you think it is. Here's the last example of wave refraction. Sunlight goes in through a raindrop. And because of the way that the waves work, they actually start to spread out based upon the different colors. At this spot in the back of the raindrop, there's actually reflection because you're going from one medium to another, and it's a special angle called 42 degrees in water. Okay, so it refracts here, reflects here, and then refracts here. And by the time the light wave comes out of here, the colors have actually separated. So if your eyeballs are right here, you would see the red part of the rainbow. And if your eyeballs are right here, you would see the purple part of the rainbow. So what really happens when you guys see the rainbow, if you would, if you were standing right here where my mouse is, the bottom part would be purple because the purple will come this way, and the red part would be on the top. That is why when you see a rainbow, it's always the red is on the top because that's how it affects your line of sight. That concludes our lecture on basic EM waves and how they're produced. The next video that you guys are going to see describes the different types of photons that are out there.